5.3 angle bisectors of a triangle. The objective is to use angle bisectors to find distance relationships. An angle bisector is a ray that divides an angle into two congruent adjacent angles. Picture of that would look like this. So this line is my angle bisector. It divides the ray into two congruent adjacent angles. Looks like that. The shortest distance from a point to a line is the length of the perpendicular segment from the point to the line. If I draw a line and put a point out here, the shortest distance is the perpendicular distance. Like that. The angle bisector theorem says if a point is on the bisector of an angle, then it is equidistant to the two sides of the angle. So we're given point X on an angle bisector AR. So here's the point. It's on the angle bisector. The distance to these sides is going to be the same. We know the distance is the perpendicular distance. So here's what happens a lot of times when people are working with angle bisectors and they want you to indicate the distance. They'll draw a line straight across, right? And they'll say that's the distance from X to the sides. That's not the distance because it's not perpendicular. What it should look like is this. Those lengths, those are the perpendicular distances from the point on the angle bisector to the side. Those distances, as indicated with the black hash marks, those are the same. Those distances are the same. That's the angle bisector theorem. Any questions on that? The converse of the angle bisector theorem says if a point is in the interior of an angle and it is equidistant from the sides of the angle, then it lies on the bisector of the angle. X is in so we've got this picture, right? In this case, the first thing we know is the yellow line. X is equidistant from the sides. As a result of that, then I can say that this angle is congruent to that angle. The red line is the result of the theorem in this case. That's the converse. Any questions? No questions. Everybody have it? No? Still writing? Okay, moving on. So here we're supposed to find the measure of HFJ. What would HFJ be? Seth, what would HFJ be? This angle right here. What would this angle right here, what would that be? Yeah, it's 23. GFJ, this is an angle bisector. I know that because of these perpendicular segments are the same. They're both 8, right? So that's that. I know that this line is the angle bisector, and so if the angle from the angle bisector to the side is going to be the same for both. This is 23, so the other side is going to be 23. For what value of x does point P lie on the angle bisector of ABC? What theorem establishes this? How could we figure out the distance from P to the angle bisector of AB, or for P to be on the angle bisector of angle ABC? What would I do? Gage, what would I do? How would I find x?
You would take x plus 8 equals 2x minus 6 and
Yeah, that's right. You're right. We'd set these two equal to each other because they're going to be the same distance. So we would so to solve for x, we would take x plus 8 equal to 3x minus 6. So that would be, we move the x over and the 6 over, so it would be 14 equals 2x. So x equals 7 would be the value of x that makes those two lines equal. Okay, what theorem establishes this? That the P is equidistant to this. The line P on the angle bisector is equidistant to the sides of the angle. Which one is that? Is that the angle bisector theorem, or is that the converse of the angle bisector theorem? Gage?
angle bisector theorem.
Yes, that is the angle bisector theorem. That one's the angle bisector theorem. All right, this says it's the converse of the angle bisector theorem. Let's go back and look. Maybe we get those mixed up. So the angle bisector theorem says if the point is on the bisector of the angle, then it is equidistant to the two sides. And then the converse is if it isn't, it is equidistant, then it lies on the angle bisector. So let's look at our question again. For for what value of x does the point P lie on the angle bisector? Okay, so we're trying to establish that BP is the angle bisector, so it would be the converse. Is there enough information to conclude that QS bisects angle PQR? Do we have enough information here? What are we missing? What's missing, Jacob? Which angle?
Oh, it'd be where S is.
That's not where we're missing an angle. What are we missing? Before we could say QS is the angle bisector, what would we have to, what do we have, what's missing about these distances, PS and SR? They're the same distance, but what are they missing? What do they have to have, Kennedy?
They need to be right angles?
Yes. We have to have right angle. We have to have a right angle here and a right angle here. We don't have that. So we don't know if that's the shortest distance or not. So that's what's missing. Okay, so here we have a soccer goalie's post relative to the ball, and the goalpost forms congruent angles as shown. All right, will the goalie have to move farther to block a shot behind the goal, right goal post, or left goal post? What do you think? He's standing on the angle bisector. Right? As marked. He's standing on so he's like a point on the angle bisector. Will he have to move farther one way or the other? You're shaking your head no, Aaron. Why not? Yeah, he'd be equidistant from each goal post. Same distance for each shot because he's on the angle bisector. That's the angle bisector theorem. Okay, concurrency of angle bisectors of a triangle. The angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle. So in this picture, AP, CP, and BP, the black lines are your angle bisectors. They're marked with these, we know that from the markings. And so they meet at this point. We're going to define that in a minute. It's called the incenter. But the incenter, this point, is equidistant from each side, as shown by the blue line. Remember, in our circumcenter, the point we did last time, it's equidistant from the vertices. This point is equidistant to the sides. That's the difference between angle bisector concurrency point of concurrency, and the perpendicular bisector point of concurrency. The point of concurrency is called the incenter. Point of concurrency of three angle bisectors. Incenter. The incenter will always be inside the triangle, whether it's right, obtuse, or acute. A circle drawn using P as the center and a distance to one side as a radius will create an inside circle in the triangle. So, there we have it. If I use P as the center, and my radius is the distance from the center to one of the sides, and I draw the circle, that's the inscribed incenter. And it's the inscribed circle, with the incenter as the center. All right, so in this question, in the diagram, P is the incenter of a triangle ABC. FC is 12, CP is 13. We need to find EP. Any ideas how we could find EP? Or do we have to find first before we can find EP? What's the only thing we can find in this picture? FP. I can find FP using what? It's a right triangle. Pythagorean theorem. So we're going to find FP with the Pythagorean theorem. So we would have, with the Pythagorean theorem, we would have 12 squared plus FP squared equals 13 squared. So that's going to be 144 plus FP squared equals 169. So FP squared equals 25. FP equals 5. Now, FP is 5. So what's EP going to be? Carly, if FP is 5, what's EP?
5.
It's 5, right, because this is the end center, it's equidistant to the side. So EP would be 5. Any questions? All right. So, compare and contrast end center and circumcenter. The end center is constructed by 3 angle bisectors. The circumcenter is constructed by 3 what? 3. Logan? No, not 3 vertices. You use the 3 vertices, but what? Yep. Not midpoints. What do we construct with the fish construction? What are we constructing there? Evan, why don't you take your earplug out? Thank you. You're using it for what? Okay, well then you don't need to have it in. What is the circumcenter constructed by?
The sides.
Nope, it's constructed by the perpendicular bisectors, okay? Perpendicular bisectors construct the circumcenter. Create segments that are equidistant from the end center to the... So what's the end center equidistant to? Is it equidistant to the vertices or to the side? End center. The one we just learned today. It's equidistant to the what, Eric? Sides. And the circumcenter is equidistant to the vertices. So that's the differences. End center is always located where in the triangle? The name tells you. Inside the triangle. The circumcenter may be located outside. If it is a obtuse triangle, it's outside the triangle. Similarities. They are both points of concurrency. Concurrency means where 2 or more lines meet. All right, any questions? I think that's it. So construction time, we'll do some constructions here from the notes.